Alright, hi, welcome back. My name is Dr. Claire, and in this video we're going to work through some examples of integrals where we compare u-substitution to integration by parts. So I've heard from students that it can be hard to tell when to use integration by parts and when to use u-substitution when solving integrals. So I just want to show you some examples and how I go through them in order to determine which method to use. So let's review the methods really quick before we get started so that you can see the two methods and know what we're working with. I have a PDF in the description that has the examples we're going to be working through, as well as my completed solutions. So you can look at those if you want to follow through, or if you need to reference it later, the notes are there for you. So let's look at u-substitution and integration by parts. So there are other techniques for solving integrals, but I'm focusing on these two today because I think it can be hard to tell them apart, specifically when you're given an integral to determine which method to use. So let's look at the two methods. We have u-substitution, and my way that I think of u-substitution is that we're starting with a function that has one variable, like let's say a function of x, and then we're going to rewrite it as a function of a different variable. So we do a substitution where we rewrite it, let's say, as a function of u. And part of what's happening when you do u-substitution is that you're undoing a chain rule derivative. So a chain rule derivative has a composition of functions, so like f of g of x, and then you're taking its derivative. And you do that by taking the derivative of the outside function, so you do f prime, and then you leave the inside function g of x alone, and you multiply by the derivative of g, the inside. So what we do when we do u-substitution is we try to identify that g, that inside function, and its derivative, g prime. So that's like our u and our du is what we're finding. So I just mentioned this because in all of the examples, I'm going to have us check our work. And when we check our work, we'll be taking a derivative. And if the derivative is a chain rule derivative, that probably means we were using u-substitution. So that's just one way to think about it, is that chain rule derivatives go with u-substitution antiderivatives. You know, it's probably not always true. I don't want to make a statement that it always works that way when I'm not 100% sure. Okay. Then we have integration by parts. So what integration by parts does is it takes a function where we have u and then the derivative of a different function v. So u dv. This really means that we have like two things going on. We have a u and a v, like a dv, and they're unrelated. So in u sub, we usually relate u to its derivative, du. We have u, we relate it to du. But here we have u and dv. So it's sort of like the two things we have going on aren't related by a derivative. So we take u dv and we rewrite it as u times v minus the integral of v du. So for me, I interpret this as undoing the product rule. We're really like undoing half of the product rule, but this formula for integration by parts comes from the product rule, and so we're undoing a derivative that happened with the product rule. Again, there are probably other instances where we use integration by parts that aren't product rule. I'm not 100% sure on that, but this is a general rule we can follow. If someone knows the answer to that and you're watching, leave me a comment and let me know. Does integration by parts always go with product rule? Does u-substitution always go with chain rule? Maybe give me a counterexample or let me know why it's true. I'd love to know. Okay, so if we think about the derivative of a product of functions, let's say f times g, that derivative is f times the derivative of g plus the derivative of f times g. So we take one derivative, multiply by the other function, and then swap that. And so when we do the integration by parts, part of what we're doing is just taking one of those terms and moving it to the other side. Then it starts to look more like our formula. So we have the derivative of f times g, that's our uv in our formula. Then we're subtracting f prime times g, that's our v du. So you can imagine integrating this whole thing. That's a little hand wavy, but that's where this is coming from, is we're looking at just one part of the product rule and moving stuff around from there. Okay, so when we check our answers, we'll likely be using product rule if we used integration by parts. All right, so let's do our first example. So here we have x times e to the x squared dx, and we're trying to find the antiderivative. We're taking the integral. What I try to do whenever I'm solving an integral is the first thing I try to do is u-substitution. I think u-substitution is one of the most straightforward options for us, and if I can do u-substitution, I'm really happy. So on all of these, we're going to try u-substitution first, and if it doesn't work, then we'll try a different method. In this video, the other method's always going to be integration by parts, but hopefully you get the idea. We're going to start with u-substitution, then look to other methods. Obviously, if we could just directly integrate this, like if it was just e to the x, I would know that antiderivative, but here we have more stuff going on. So let's try u-substitution. I'm looking for sort of the inside function where I might see its derivative. And I get excited because I see an x squared in the exponent and an x. And I know when I take the derivative, I lose a power. So like the x squared becomes a 2x. So that makes me feel good because I have an x squared and an x. So we're gonna just try u equals x squared, and then we find du, so we find the derivative of that. So here, the derivative of u is 2x dx, and this is what we're going to be using for our substitution. So depending on how you like to do this, I'm going to solve so that I have 1/2 du equals x dx. So I've just divided that 2 over to the other side. Now I have my x dx in the original integral, and I'm going to replace that with my 1/2 du, and my x squared gets replaced with u. So let's write that out. Now I have the integral of e to the u, that's e to the x squared, e to the u, and then the x dx gets replaced with 1/2 du. I'm feeling good now. So we got rid of all of the x's and we just have e to the u with a constant, but we can integrate e to the u. We feel good about that, hopefully. All right, so when we do this, I'm going to get 1/2 e to the u plus c. So e to the u is its own antiderivative. So the antiderivative of e to the x is e to the x, and that's because the derivative of e to the x is e to the x. So those two kind of just bounce back and forth. And we have that 1/2 that it is being multiplied by. And so we've done our antiderivative, and now I just need to plug in x squared for u. So I have 1/2 e to the x squared plus c. And there we go. Cool. So this one, we just tried the u-substitution, see if it works, and then we don't need integration by parts because this worked just fine. We were able to get rid of everything and replace it with u, so there were no x's left over. That's what I mean when I say get rid of everything. So what I want us to do is just check our answer. So I think this is good practice for while we're doing this. And what I mean by check our answer is we're going to take our antiderivative, our integral. I'm using those words interchangeably. I bet some mathematician's going to be real mad about that. I mean, I'm a mathematician and I'm not mad about it, but anyway. All right, so let's take our 1/2 e to the x squared plus c and find its derivative. So we're going to take its derivative just to check. So we have the derivative of 1/2 e to the x squared plus c. And when we take its derivative, we should get back to the original function we were integrating. So I do a chain rule on this. I take the derivative of the outside function. The outside function is e to the something. So I leave that as 1/2 e to the x squared. And then I multiply by the derivative of the exponent. And the derivative of the exponent is 2x. So I have 1/2 e to the x squared times 2x. And then the plus c, that derivative is always 0 since c is just a constant. Derivative of a constant is 0. And now when I simplify this, I should see that I'm getting x e to the x squared, which is good. That's what we started with in our original integral that we were trying to solve. Okay, so now I'm going to show you an example that looks slightly different, and it's going to require, probably the other method, right, if you're following along here. But the idea is that just a small change in the problem can make us need to use a different method. So now instead of e to the x squared, we have e to the x. So we're looking at x, e to the x, dx. And if you've learned integration by parts recently, this is a really classic example that gets brought up, so you may have seen this before. But let's just try to think about how we might do this with u-substitution. So, I mean, maybe you're like, I'm not really sure. Can I let u be x? Can I just do a u-substitution? Well, then du is 1 dx. And so I could then rewrite this whole thing as just u, and then I'd have e to the u du, but that didn't really do anything, right? I just replaced all the x's with u's. So maybe we try to do e to the x as our u. So we have u equals e to the x, then du equals e to the x dx. So here I have the e to the x would get replaced, but I'm still left with this x out front. So in this case, I'm seeing that the two functions I have going on, I have an x and an e to the x. They're not really related by a derivative. So before we had e to the x squared, and I could see how they were related by a derivative. The derivative of x squared is 2x, which kind of showed up on the outside. But here, these two don't seem as related by a derivative. It's not clear to me that like the derivative of x is e to the x or vice versa. Okay, so when I can't figure out a u substitution, it's great to then go to an integration by parts. And integration by parts, since it's related to the product rule, often happens when we have a product of functions. So here I'm seeing x times e to the x, which to me is a good indicator that I'm going to be using integration by parts if I can't do u substitution. And now we need to pick our u and our dv. So those are the two things we find, and then we compute the v and the du. All right, so there's a little acronym you can use when you're doing integration by parts. It's LIATE, LIATE. They each stand for something, each of the letters do. So it's logarithms, inverses, algebra, trig, exponentials. And the important thing here is that like exponentials are your last choice usually. That's the only reason I even mention this. And the idea is that when we do integration by parts, we're hoping to somehow change the problem we're looking at. And if we just use e to the x as our u, when we take its derivative, it stays the same, right? It's still e to the x. So for u, we want to choose something that's going to shift, that's going to change, that's going to like somehow become easier or different. So I'm going to choose x as my u, and then I'll choose e to the x dx, that's the remaining part, as my dv. Now we compute du, the derivative of u is just the derivative of x, which is 1 dx. And now we compute the antiderivative of dv to get our v, and that is e to the x. So we've essentially gone from x down to 1, and then the e to the x stayed the same. You can always try the other way around, right? Like you can, like very commonly when I do these, I actually pick them wrong on accident, and that's fine. You know, we have to choose a u and a dv, that's how the formula works. But you can choose them wrong, try it out, then you're gonna get stuck, and then just go back and try the other one, that's fine. Okay, so here we rewrite our integral. So we are starting with u dv, and now we're going to rewrite it as uv minus the integral of v du. Okay, so let's do that with what we've chosen. So u times v is x e to the x, and then we subtract our integral of v du. So v is e to the x, and du is just dx. Okay, and I'm already feeling good. So I look at that new integral. That new integral is just e to the x. Beautiful, I love that. I know how to do that. I've already done that in this problem actually. So okay, we're almost there. Let's just solve this. So I'm left with x e to the x on the outside, and then I compute this integral. We subtract this integral, which is just e to the x, and we put on our plus c, and we're done. So that worked great, I think. We picked our u and our dv, we did integration by parts, and we were able to do the integral we set up. If you've set it up wrong, you probably won't be able to integrate. We'll see one later that you won't be able to integrate and you did it right, but anyway, just know that like you can always try again, swap them around. All right, and we are going to check our work. So we're going to check our work by taking the derivative of this just to really make sure we know that we did it correctly. So we're taking the derivative of x e to the x minus e to the x plus c. So you'll see we're using a product rule, which is a good sign. So the product rule on x e to the x, let's take the derivative of x first, that's 1. Then the derivative of e to the x, that's e to the x. Then we're on the next part, so now we're subtracting the derivative of e to the x, that's e to the x. And the derivative of c is 0. Okay, so we did product rule on that first part and then just another derivative. And you'll see here that the e to the x terms are canceling out, which is great. So we're left with x e to the x, which was what we started with. Cool. So that's part of how the integration by parts works, is that we're subtracting off that part in order to get back to what we started with in the derivative, I guess. I don't know, not sure if that helped, but I like doing the checking just on these problems. I think it can really solidify that we're doing things right, and we get some practice doing both antiderivatives and derivatives, which is good. All right, let's do another example. Now we're looking at the integral of x ln x. So I'm going to stick with my method of trying u substitution first. So let's go ahead and do that. So I'm going to maybe choose u as ln x, just because like it's complicated. I could take its derivative and maybe I can somehow do something with the x. So then when we do du, this is 1 over x dx. Okay, and so this might lead to something since there's an x and an ln x in the original. Maybe, I mean, I know what's gonna happen, but let's try. So let's maybe solve for dx. So x du is equal to dx. I've just multiplied that x over. And now let's rewrite our original integral. So now instead of ln x, we have u. And then instead of our dx, we have x du. So unfortunately, instead of canceling out with that x we had in the front, it is just further adding to the situation. So now we have an x squared u du. So that would be x squared u du. And I don't really know what to do from there. So actually when I did this on my own firsthand, I tried some like other things with the substitution. I was like, can I take the u-substitution and exponentiate it? And I mean, you can, but at the end of the day, we always end up having to do integration by parts, at least from what I can tell. So this didn't work out. We weren't able to do a u-substitution, at least not easily. And so I'm going to just say, okay, that didn't work. Let's try integration by parts. And part of why I think that's going to work is that we have an x times ln x. It's a product. The integration by parts is related to product rule, whereas u-sub is good for chain rule. So let's try it out and see what happens. All right, so for integration by parts, we need to pick a u and a dv from our original. So if we remember our acronym, the LIATA, L is the first thing, that's the log, our natural log here. I love to choose that because when we take its derivative, it goes to 1 over x, we get rid of that function, natural log, and we have something easier to work with. So I am gonna choose ln x as my u here. And now instead of doing just a u substitution, we're also gonna pick dv. I'm gonna choose x dx, that's everything left over, as my dv. Now from here, I compute du and v. All right, so the derivative of natural log is 1 over x dx. And then we're taking the antiderivative of x dx, and we're just gonna get 1/2 x squared. Okay, so using these as our substitution, we are now going to rewrite this as uv minus the integral of v du. So now we just need to replace the uv v du with what we've decided the substitution is. So u is ln x, v is 1/2 x squared, then we subtract a new integral, and hopefully that new integral is something we can solve. So we have v, which is 1/2 x squared, and then du is 1 over x dx. And I'm feeling good about this because this new integral just has x's. There's no natural logs, no other complicated things. It's just algebraic, it just has x's. So we should be able now to simplify this, solve the antiderivative, the integral, and get an answer. So I'm gonna leave the beginning part the same. I'll just reorder it, 1/2 x squared ln x. Then we subtract this integral. I'm gonna write the 1/2 on the outside, and then my x squared and my 1 over x reduce, they become just x. So one of the x's cancels out. And I have x dx as my integral, which that is so beautiful. We would love to take the antiderivative of things like x dx. That's amazing. We've actually already done that today. It's interesting, both of the examples had that happen, where the integral we were left was actually our dv. Pretty cool. Okay, so when we do this, we get 1/2 x squared ln x, then we subtract 1/2, and we do this integral. The integral of x is just 1/2 x squared, and then we'll have our plus c. So altogether, I'm getting 1/2 x squared ln x minus 1/4 x squared plus c. And there we go. So the integration by parts worked. It got us to an integral we could solve when we did a substitution. All right, I do want to check this by taking the derivative, so let's try that out. We're gonna take the derivative of what we just got. If you're not interested in this part, you can skip ahead to the next example. I just like doing this to really make sure, but this derivative will take us a second to work through. Oh, right. So the first derivative we're doing is a product rule, since we have x squared times ln x, which makes sense. That goes along with our integration by parts. So I'll do the derivative of the 1/2 x squared first, that's just x. Then I do the derivative the other way, so I leave the 1/2 x squared alone, and I do the derivative of ln x, which is 1 over x. So that's my product rule. Now I have the derivative of the 1/4 x squared, so I'm getting minus 1/2 x. And then the derivative of c, since it's a constant, is just 0. All right, now we simplify. So I have x ln x. That's what we're ultimately hoping to have. That's what we started with in the original problem. So we're hoping the rest of this cancels out, which it should. So one of the x's cancels in this next part, so I have 1/2 x, and then I subtract the 1/2 x. Perfect, it cancels like we wanted, and I'm left with x ln x as my derivative, which confirms that we did the antiderivative correctly. So that's that problem. We tried u-substitution, it didn't get us anywhere. We just did the integration by parts because we saw a product and it worked out. All right, so this time we have the integral of 1 over x ln x. And so this looks similar. We've just taken everything we had before and put it into the denominator of a fraction. All right, so I am going to try a u-substitution first again, and we're going to pick u as ln x, just like we've been doing every other time. And without doing much else, I'm just gonna try this out, see what happens, not get too scared, see if I can cancel things out and have it work. So if u is ln x, then du is 1 over x dx. And oh man, I'm happy because I see a 1 over x in the original problem. So even if you don't see that right away, we can do another step here. Let's say you just want to solve for dx so you can replace it in the integral. We would multiply the x over so that we have dx is x du. Okay, so now we can go to our problem and rewrite it. So I have 1 over x, I'm replacing ln with u, and then my dx I'm replacing with x du. So I've replaced ln, and I'm also replacing dx. Okay, now we can see that the x's are actually going to cancel, which is great. That tells us a u-substitution is working when we are getting rid of all of the old variable and replacing everything with the new variable. So I'm now left with the integral of 1 over u du, which is amazing. We can do that integral. The antiderivative of 1 over u is just ln of u. Cool. So antiderivative is ln of u. I'll use absolute values just to be like super careful since natural log can't take in negative inputs. And then we do a plus c. And then we just gotta replace the u, right? So we got this back in terms of u. We know that u is ln x, so this is really ln of ln x. Kind of a cool result. And then our plus c. And there we go. So this is a great time for us to check our answer. We're taking the derivative of ln of x. This is one of those cases where we write the absolute values just to be like technically correct. I always got annoyed when in math we would just like drop absolute values and act like they didn't matter. What's really happening here is we're just saying like only look at part of it, like only look at the part where it's positive because it's the only part that works, and that's why we can kind of just drop it. It's more of like a if you were looking at this later, you'd want to just look at the positive part, but everything else works right. We're doing like just half of it. It's maybe not half, right, but we're just taking like part of it. So all the same rules follow. Okay, anyway, that's just my tangent on randomly dropping absolute values, which I'm gonna do right now. Okay, so the outside function is ln, so we do the derivative of that. So we do 1 over whatever on the inside. So we do 1 over ln x. The outside function is natural log. The derivative is 1 over whatever the input is. Then we multiply by the derivative of the input. So multiply by the derivative of ln x. So that's chain rule. Derivative of the outside with the inside left alone times the derivative of the inside. It's just confusing because everything's ln here. Okay, and then the derivative of the plus c is 0. Okay, so we have 1 over ln x. Then the derivative of natural log of x is 1 over x. And there we go. So I'm getting 1 over ln x times 1 over x, which when we put these together is just 1 over x ln x, which is what we started with. Cool, there we go. Okay, we have 2 more examples to look at. Let's check those out. This time we're looking at integrals that involve trig functions. This first one is the integral of sine times cosine dx. So since we have a product of functions, you might think that we're going to use integration by parts, but my suggestion is always to start with u-substitution and see if it works out. Especially since here we know that sine and cosine are related by a derivative. In some of our other examples, it wasn't as clear if they were related by a derivative, like x and e to the x. But here we have sine and cosine. We know those are related with a derivative, so I think a u-substitution might work, and it's worth trying first before we go into integration by parts. So to choose our u, I actually think we could choose either sine or cosine. I'm going to choose sine though, and my reason for choosing sine of x is that when I take its derivative, I get my du. There's no negatives involved, so the derivative of sine is just positive cosine. And I like not having extra negatives to deal with because it's kind of easy to get lost or mess those up in some way. It's just extra math to worry about. But we could maybe choose u as cosine, its derivative is negative sine, and that would probably work also. And all right, I'm feeling good about this, right? Like this is actually a pretty straightforward one. We have sine and cosine dx, and that's everything we had written here. So when I go to rewrite this integral, I now have the integral of u du. And it's as simple as that. So we had sine and we had its derivative cosine, and there we go. So when we do the integral of u du, we're adding 1 to the exponent and dividing by the new exponent. So I have 1/2 u squared, and then I'll do my plus c. And as our last step, we have to go back in and put in for u what our substitution was. So here our substitution is sine x. I'm going to write sine squared x with that squared on the inside just because that's how I like to do it, and that's kind of the cleaner way. All right, so 1/2 sine squared x plus c is our antiderivative. Cool. So it might not be super obvious that this is the antiderivative, and that's why I love checking. So let's check our answer. We should see here, since we did a u-substitution, that we're doing a chain rule as part of our derivative. So when we take the derivative of our answer, that's 1/2 sine squared of x plus c. We really have that squared on the outside. So I don't know, maybe I should have kept it with that on the outside. No, I'm second guessing myself. So we do 1/2 sine of x, and that's getting squared. These notations are equivalent, so you can always do them both. It's really just up to what feels better for you. Okay, so we have something squared and the inside function is sine. So when we go to do the derivative, we do chain rule. The 2 comes down in front. We leave the inside alone. And then we decrease the exponent by 1. So I have 1/2 times 2 sine of x. And then I would take the derivative of the inside. So I take the derivative of sine. As always, r plus c, the derivative of that is 0. Okay, so my 1/2 and my 2 cancel. I'm left with sine x times the derivative of sine, which is cosine. And there we go. We're back to where we started, which is good. So here we did a chain rule, which corresponds to our u-substitution, and that's it. All right, so I'm going to show you a very similar problem. I've now just replaced the cosine with a sine. So I have the integral of sine times sine. And it would make sense that if you saw this in like a math textbook or if a teacher gave it to you, it would probably just be written as sine squared x. But I just wanted to write it as the 2 things multiplied together because it relates it back to that example we just did. And that's actually how we're going to solve this, is by splitting it up. So I'd say this is kind of the most challenging one that we're going to do. I think it's really cool math. It makes me I love integrals, so this is what I love about doing integrals. So it's like a little puzzle. Okay, so just something as simple as changing the cosine to a sine is going to involve some more steps. And you can probably kind of feel it if you've done a lot of integrals when you look at this, that it's not going to just be simple. Like we can't just let u be sine, because then we would need du, which is cosine. And what do we do with that? So I don't know, I'm going to walk you through like what you might try if you didn't know and you just tried to do u-substitution. So let's say you even just let u be sine, and du is cosine of x dx. Now, when you go to rewrite the integral, you're going to have u squared But then dx is going to be like 1 over cosine du. Okay? And then 1 over cosine is secant. But what are you gonna do with secant? Right? Like now we have an integral that has a u and a secant in it. Not great. So we basically just like introduce another trig function in here. So my method is going to be to abandon u-substitution. Like I tried, I don't know, it didn't get me anywhere. Maybe there's a way to do this. And honestly, there might be a way to do this, right? Integrals often have multiple ways to solve them. But I have other tools I can use. I have other methods. And so let's try one of those other methods. Namely, let's use integration by parts. This is a video on integration by parts, so it makes sense. Okay. For integration by parts, we pick our u and our dv, and then we find the corresponding other components. So if I have sine times sine, I'm just gonna have to use sine as my u, right? There's no other option. So if sine is u, sine dx is also our dv. So I'm basically taking both parts of this and making them the u and the dv. All right, then we need to find our du and our v. We compute those on our own. So the derivative of sine is cosine. So du is cosine x dx. And then v is the antiderivative of sine. So the antiderivative of sine is negative cosine x. Should make sense, right? The derivative of cosine is negative sine. Those negatives will cancel. If you need to take a second and do that as like a separate step, it's totally fine. So taking the antiderivative of sine, that's negative cosine. All right, now we have all of our components and we just need to put them in to our formula. So we do uv minus v du, the integral of v du. All right, and I'm optimistic this will work, we'll see. It's hard, I already have done this right, and I'm so excited. Okay, let's go ahead. Okay, so our u is sine. I'm just putting the components in where they go. And the v is negative cosine. Then we subtract an integral. That integral is negative cosine x. And then the du, which is also cosine x dx. Okay, so I'm seeing a new integral that has 2 cosines instead of 2 sines, which is a little concerning, right? It's very close to what we started with. But one of the things that often happens in integration by parts is that we get a new integral that's related to our original integral, and we can do some cool math with it. So let me show you. I want to simplify the first part. So sine times cosine, we'll just write those together as negative sine cosine. That part is done, that'll stay there. Then my negatives, I'm going to rewrite as a positive integral, so plus the integral of cosine squared dx. So we have cosine times cosine, that's cosine squared. Okay, so I still don't know how to do that. What I'm going to do at this point is actually use an identity. So this just really is a lot of having done a lot of these, thinking like, where am I gonna get to? How can I relate this back to the original? So at this point, I think if you're new to doing integrals, you'd probably need to take some time and try this out. Maybe you do a second integration by parts. Maybe you open up a program and you find the antiderivative using technology, and then you kind of work backward and figure out how you got here. There really is some practice that goes with this. And even before we had computers, they had these huge books that were just tables of integrals where you would look up, like in these 1,000 pages, your integral you were looking for, and someone had already done it and had the answer. So there's really no shame, in my opinion, in looking up the answer in order to help you learn the process. So you can always try on your own, try some stuff out, but if you get stuck, like, go ahead, get some help. So I saw that we had a cosine squared here, and I've done enough integrals that I was like, I think I can relate this back to the original, which was sine squared, because I have an identity, it's the Pythagorean identity, that relates sine squared and cosine squared together. So let's take like a little pause in the middle of this, and we're gonna do that. Gosh, I'm trying to like explain myself, but I'm so excited. Okay, so we're looking at the Pythagorean identity, which is that sine squared plus cosine squared equals 1. And so using this, I can rewrite to get a equation in terms of cosine. My goal is that I want to take my cosine squared that's in my integral and replace it with something to do with sine squared. This gets me like all similar things going on so that all of my integrals, including the one I started with, all have a sine squared in them. So that's what we're working on. Now, that's going to look like moving the sine squared over to the other side of this identity. We're doing kind of some scratch work that isn't related. It's like not part of our integral itself. So I can now say that cosine squared is 1 minus sine squared. And what I'm going to do now is go back to my integral and rewrite it with this in there. So my negative sine x cosine x stays. And then when I look at my integral, I'm going to replace that cosine squared x with 1 minus sine squared x. Okay, now I'm seeing that we have a sine squared, which is related to our first integral that also had a sine squared. So I'm going to split this up. I can take the antiderivative of 1. That makes me feel good. So let's succeed at that, and then we can move to the next step. Again, I have done this ahead of time, so I'm seeing it. But if you haven't done this type of problem before, it might seem like magic. And I don't know, that's part of what I like about these problems is that you practice them, you see someone try it out, and then it becomes more obvious to you or clearer to you how you might repeat something like that in the future. Okay, so I've split up my integral. I have the integral of 1 dx, and then I subtract the integral of sine squared. And that integral of 1 dx, let's just get that completed. So that integral is just x, okay? And then we're subtracting the integral of sine squared x. All right, so this is where things get interesting. This is a very specific type of situation that comes up when we do integration by parts, where we now have an integral that looks just like the integral we started with. So I like to kind of pause, take a moment, and rewrite my entire statement as what I have so far. So what I'm working with is I have the original problem I was trying to solve, which is the antiderivative, the integral of sine squared x dx. And I've done a bunch of math to show that that's now equal to this other thing. So it's equal to negative sine x cosine x plus x minus this integral. And this integral, sine squared x, matches the one on the other side of the equation. Okay. So I have a sine squared x integral on both sides, and I'm going to put them together. So I'm going to move one of them over to the other side. So when we move one of the integrals over to the other side, we now have 2 of those integrals. So we're taking one integral plus another of the same thing. So we get 2 of them. All right, and now we can solve for our integral by dividing by 2. Oh my gosh, I love it. So we're gonna eventually get our integral of sine squared is equal to something. And we're doing that by now dividing by 2. So I'm now showing that the integral of sine squared x dx is equal to negative 1/2 sine x cosine x. That's me dividing by 2, it's just multiplying by 1/2, plus 1/2 x. And we did it. We also need a plus c. I think somewhere in there I lost my plus c. So we'll just put it on at the end, okay? We gotta have that plus c. And there we go, we did it. So, you know, I'm gonna have us check this, but I just think this is so cool. And again, this takes practice. This is why we did this last. Seeing that you need to use integration by parts and split it up and move it around this way, just take some practice. All right, so let's check our answer. We're going to take our solution and find its derivative to make sure that we end up back at sine squared. So I'm taking the derivative of negative 1/2 sine x cosine x plus 1/2 x plus c. And similar to every other time we've done a problem with integration by parts in this video, we're going to be doing a product rule in our derivative. So we have sine times cosine. So to take that derivative, let's do the derivative of sine first. Derivative of sine is cosine. Then we add it to the other way around. So we leave sine and we take the derivative of cosine, which is negative sine. So that just takes a little bit of being careful. We take the derivative of sine is cosine, derivative of cosine is negative sine. I've done my product rule now. And then I add the derivative of 1/2 x, which is just 1/2. And as always, the derivative of plus c is just 0 since c is a constant. Okay. Now we're really hoping that we can get back to sine squared, and oh my gosh, we're gonna do it. It's so cool. But to show that it works, it does involve the Pythagorean identity. So if you're tired at this point, I totally support that. But I wanna show you how we get back to where we started. We're gonna have to use that identity again. Okay, so I have negative 1/2 cosine squared x plus 1/2 sine squared x plus 1/2. All right. So I'm going to go back and replace my cosine squared x with what we said it was before, which is 1 minus sine squared x. So it's the same replacement we did earlier. We're going to do it again. And then when we simplify everything, we should be left with just a sine squared x. So that's why I'm moving the cosine into being sines, because I know that what I'm trying to show is that this is all equal to sine squared. Okay, we're almost there. So we put in 1 minus sine squared x. And now we're just going to distribute that negative 1/2 on the outside. So I'm getting negative 1/2 plus 1/2 sine squared. Then I have another 1/2 sine squared and a 1/2. So the 1/2s go together to be 0, so let's cancel out. And then my two 1/2s go together to be 1. So I'm left with just 1 sine squared x, which is what we wanted. And that's what we started with, that's what we were trying to find the antiderivative of, and we did it. All right, there we go. So that was a really long one, but just changing the problem a little bit created a much more difficult problem. And that's what I think is really unique about integrals. There's not like a clear way to look at it and know how complicated it's going to be. Whereas when you're doing derivatives, there's like a process you follow, right? You use the product rule, you use the chain rule. But when we do antiderivatives, we do integrals, there's not as simple of a way to know what rule to do. You really have to try things out and see what works best. So, all right, there's some examples of doing either u-substitution or integration by parts and trying to determine which method to use. Remember to always try u-substitution first, and if it doesn't work and it seems like you have a product of functions, give integration by parts a shot. All right, thanks so much for watching, and I'll talk to you in the next one. Bye.